Hi everyone, we are MSc Net Zero Building Services Engineering students from Loughborough University, and we will be presenting our submission for the 2025 SETTY Family Foundation Net Zero Energy Design Competition. First and foremost, I would like to introduce my fellow colleagues, Jessica, Tin, Minus, John, Tabiso, Kevin, Samuel, and myself. The presentation structure will include the basic building design and site analysis, site sustainability, building construction, lighting strategies, HVAC system, BMS system, renewable energy integration, life cycle cost analysis, and a short video summary of the final building design.
Original building design. Our target is to build a medical office in the city of Manchester. This building is for patients to access doctors but not staying overnight. We built a model in IES to evaluate the energy consumption. After the base model is complete, we also compared it with the benchmark for the validation. The bar chart shows the annual energy usage intensity of the result, which are at the same level as the benchmark. The simulation is reliable, and we can do the following design. For the site selection, we follow ASHRAE 189.1. Choose a grid field as our site. Transportation is also a key point for decision making. Climate change is an issue for building service, so we did the weather analysis such as solar radiation, soundtrack, wind direction, and water resource to support the design strategy.
The design choices made to achieve site sustainability aim to benefit both the surrounding environment and building users. To satisfy the environmental needs, sustainable drainage systems such as permeable paving, soakaways, and bioretention systems have been used to increase infiltration and attenuation. French drains and swales have been used around the perimeter of the site and car park to mitigate surface runoff contamination and pollution of surface waters. The increased vegetation from the provision of these measures will create new habitat supporting local wildlife and biodiversity. With regards to improving occupant health and well-being and building experience, the improved landscape creates area for relaxation and recreation. The provision of bike sheds encourages occupants to incorporate physical activity within their day and offers a green alternative for transportation. And the implementation of a green roof and green walls continues the use of green design to provide effective solar shading and sound insulation, increasing indoor comfort.
For the baseline model, since the building is to be located in Manchester, United Kingdom, we assume compliance with the UK Building Regulations 2010 Part L, which determines the cross-sections and standard U values for each building element as shown in the table above. In the proposed model, we compared ASHRAE standards 90.1 and Passive House standards, and subsequently optimized the building's materials to achieve U values lower than those specified by Passive House, aiming for a net zero energy building. Using IES, we enhanced the design by upgrading windows from double glazed to triple glazed argon-filled and low E coating windows, as seen in the table below. We additionally increased the thermal mass of the external walls and roof, added insulation thickness in key areas, incorporated shading strategies, all with the goal of reducing energy demand.
Lighting in medical buildings went beyond visibility. It directly impacts the patient's well-being, staff performance, and the sustainability of the building. We recognized this when we started off by incorporating overhang shading devices to block out the high-angle summer sun while allowing in the low-angle winter sun for passive heating. This also helped us to reduce glare, improving the overall visual comfort for the occupants. During the analysis of the architectural drawings, we identified an atrium space that offered an ideal opportunity to incorporate an angled skylight, allowing daylight to filter deep into the building, reducing our reliance on artificial lighting during the day. This move also supports our biophilic design principle, reinforcing the connection between the outdoor and indoor environment. To ensure even lighting throughout the building, we use Radiance IES for daylight analysis. This helped us to identify areas needing additional lighting and an informed strategic placement of the LED fixtures that meet ASHRAE 90.1 standards were selected. These were selected for energy efficiency and visual comfort. To complement these artificial fixings, we also incorporated daylight and motion sensors. Together, these strategies create a lighting system that's sustainable, human-centered, and performance-driven.
The HVAC system will be designed using two peak cases, the first being the current building base case, and the second being the future expansion case, which includes the expansion of the third floor shell space, typical of the west wing of the first and second floors. The building will use a dedicated outdoor air system to supply pre-treated outdoor air, which will be further treated locally by either option 1, the VRV cassette system, or option 2, the air source heat pump chilled beam system. The HVAC components will be sized inclusive of a 10% safety margin and configured for part load and redundancies. The central DOS system will supply a base case of 16,000 liters per second of airflow with a peak thermal load of 242 kilowatts. The expansion case will have a peak airflow of 19,000 liters per second with a peak thermal load of 292 kilowatts. The DOS system will be sized for N+1 redundancy. The selected DOS unit is the Mitsubishi DOS MPE4, which has the airflow capacity of 6,400 liters per second each and a thermal capacity of 88 kilowatts, giving a base case of N equals 3 and an expansion case of N equals 4. The local air treatment will supply a peak thermal load of 34 kilowatts for the base case and 41 kilowatts for the expansion case. The VRV will be sized for a redundancy of 2N, for which the selected VRV unit is the Daikin VRV RE-YA88A, which has the thermal capacity of 22.4 kilowatts each, giving both cases an N equals 2. Similarly, the heat pump system will be sized for a redundancy of N+1. The selected heat pump unit is the Daikin EWYT CZN016, which has the peak thermal capacity of 18 kilowatts each, giving a base case N equals 2 and an expansion case of N equals to 3. As shown on screen, the capital expenditure of option 1 is 30% higher than that of option 2. Furthermore, option 1 would come with a higher refrigerant leak risk, leading to a higher operational carbon, as well as increased fire, health, and safety issues. As a result, option 2 will be selected for the final HVAC design.
In our building, the BMS isn't just a control system, it's intelligent. A cloud-based machine learning model is integrated that connects securely to the BMS through encrypted VPN tunnels and authenticated API interfaces. This model doesn't just react, it predicts. It analyzes occupancy trends, indoor air quality, energy data, and weather forecasts to proactively optimize the lighting, HVAC performance, and set point schedules. Beyond optimization, the system also handles data-driven fault detection. Unlike conventional alarms, it uses pattern recognition to detect HVAC issues before they cause failures, saving time, reducing spare parts stock, and keeping our critical environments running smoothly. And what if the internet goes down? No problem. A hybrid connection check is implemented, and if a disconnection occurs, the system automatically fallbacks to local control to prevent service disruption. In essence, this is more than building control. It's predictive, it's proactive, and it's protected.
Considering the UK Renewable Energy Development Plan and Manchester climate, we integrated a PV solar system to this project. To maximize output, panels are suggested to be south-facing with 30 to 40 degree tilt angle. We selected readily available and high-performing local products. Through Python-based parametric analysis, the 40 degree tilt was confirmed, and the system will be on the parking roof since the building roof is already planned with green spaces. Initially, more than 400 PV modules were required, but considering the grid export benefit and future rising energy demand, we've provided over 800 across the entire parking roof, as shown on the master plan. This expanded PV system is crucial for our net zero target. For the present day weather, our 480 MWh PV generation comfortably covers the building's 250 MWh annual demand. Even with future climate change scenarios that we simulated using ASHRAE data in NZBSE, this system still ensures we maintain net zero potential and can even export surplus energy, regardless the panel's performance degradation throughout their life cycle, future-proofing our net zero design.
It is very important to understand the cost of the project. This is to ensure it comes in under the strict budget set by the client. The PV was first looked at by itself. This resulted in a payback period of 5 years and when discounted 6 years and an IRR of 29%. This is very promising financial metrics showing that the PV is a good addition not just sustainably but also financially. The capex of the project is 1.1 million, mostly made up by the PV as shown here, with the chilled beam units and the direct outlet air system also make up a large amount of the capex. When looking at the lifecycle costs as a whole, the net project costs come in at £6.8 million. When discounted with a 4% discount rate, this comes in at an NPV of £2.8 million. These are both underneath the client's budget of £7.9 million when looked at over a 50-year analysis period. It is key to understand the life cycle carbon emissions of the project, as this project is about being net zero. To do this, we have to look at the embodied carbon. For this project, it was shown to be 300 kilograms of CO2 emitted per metre squared. This is to comply with the REBA Sustainable Outcomes Guide, totalling at 1.8 thousand tonnes of CO2 emitted across the whole building. When looking at the operational carbons, we can see here that the baseline building was reduced down significantly due to building improvements, as talked about previously. Any remaining carbon emissions were offset by the PV, shown here that the energy use intensity goes down to zero because of this. Therefore, the building is net zero carbon and energy in operation. Due to the excess PV export, the building can be considered to be net negative carbon in operation, making back 20% of its embodied carbon.
To summarize, we have a short video highlighting the key features of our final building design. Thank you for listening. We truly appreciate your time and expertise. It's been an honor to share our vision, and we look forward to hearing feedback from you soon.